The chemical makeup and the polarity of water gives it unique properties, and one of those properties is what we refer to as cohesion. Cohesion is hydrogen bonding of water to other water molecules. There's another closely related principle called adhesion, which is the hydrogen bonding of water to other polar surfaces besides water. Both of these are illustrated very well in trees. If we take a look at these images, this shows the process of how water moves from the roots of a tree up to the leaves. This process begins as water molecules are evaporated from the leaves. As water molecules are evaporated, they will pull on the water molecules behind them through these cohesive hydrogen bonds. And that pull is translated down the length of the tree into the roots, where cohesive hydrogen bonds between the water in the roots and the water in the soil draws more water into the tree. Adhesion also shows up in this process. If you take a look at this central image, there are adhesive bonds between the water and the sides of the tree, or the veins in which the water travels. Those adhesive bonds prevent the water from flowing backward as a result of the force of gravity on it. So when the water is not flowing up the tree, it doesn't flow out. Here's another example of cohesion between water molecules. This image is an example of surface tension, where the hydrogen bonds between the water molecules causes the surface of the water to hold together. The reason this water strider can walk across the surface of the water is because the hydrogen bonds between the water molecules are stronger than the forces that the water strider puts on them. So the bonds don't break and the water strider stays on top of the water. Another unique property of water is that it moderates temperatures, which means that it prevents temperatures from fluctuating very much. In order to understand this, we need to understand a little bit about energy and how energy relates to heat and temperature. Kinetic energy is the energy of motion, and that energy can be transferred from one object to another, much like these pool balls, and the first ball transfers its energy to the second. Water acts in much the same way. In a body of water, the molecules are constantly moving, and the movement of these molecules is kinetic energy. Now, heat and temperature are related to the kinetic energy of these molecules. Heat is the measure of matter's total kinetic energy due to the motion of its molecules. What this means is that you add up all of the kinetic energy from all the molecules in a body of water, and that gives you the amount of heat in that body of water. So heat depends on your volume. Temperature, on the other hand, does not depend on your volume. It is only the average kinetic energy of the molecules. We can illustrate the difference between temperature and heat with these two figures. Which one of these would you say has a higher temperature? I think it's pretty obvious that the pot of water has a higher temperature. But which one would you say has more heat? You might be inclined to say again, a pot of water, but you have to think in terms of the definition. The pool has a lot more total volume, and the total kinetic energy of all those water molecules is way more than the small amount of water that's in the pot. There's another term that you need to be aware of, and that is calorie, which is the amount of heat that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. We can use all of these principles in a real-life situation called coastal temperature moderation, which is what happens in California, where the temperatures are relatively moderate throughout the seasons. In order to understand how coastal temperature moderation works, we need to understand a principle called specific heat, which is the amount of heat that must be absorbed or lost for 1 gram of a substance to change its temperature by 1 degree Celsius. Now, water, we know, requires 1 calorie of heat to change its temperature by 1 degree Celsius. So that's the specific heat of water. We can compare that to another liquid, say ethyl alcohol, which has a specific heat of 0.6. That means it requires 0.6 calories to change 1 gram of ethyl alcohol by 1 degree Celsius. The reason for this difference is because of the hydrogen bonds found in water. When a body of water is cooled down, the molecules actually slow down and more hydrogen bonds form. The formation of those hydrogen bonds releases energy, or releases heat. Whereas when you heat up a body of water, it requires the input of energy, and that input of energy breaks the hydrogen bonds and allows the molecules to speed up. The significance of all this is that a lot of the energy, or a lot of the heat that is put into a body of water, is used to break the bonds between water molecules and is not translated directly into the kinetic energy of the individual molecules, so it doesn't heat up as fast. So it requires a lot more energy to break all those bonds and speed up the molecules. Where the reverse is true also. As a body of water cools, it gives off a lot of energy because a lot of hydrogen bonds are forming. Now, if we look back up at this middle picture, we can relate this to the coastal temperature moderation. Throughout the day, heat is given off by the sun, and a lot of that energy is absorbed by the water and not into the air. So the water will absorb a lot of that energy, and slowly throughout the day will increase in temperature. The reverse happens at night. When the temperature drops, the water is warmer than the air and will give off energy or heat into the air as the water will begin to cool down and the air around it will begin to heat up. Now this happens relatively instantaneously, and so you don't notice it very much when you're there, but this is how the coastal areas in California stay moderate throughout the seasons. And you can see from this map, as you go inland not very far, temperatures start to fluctuate a lot more dramatically just because they're not right next to the water and they don't experience this moderation of temperature. Another unique property that water has is that it expands when it freezes. As it goes from a liquid to a solid, it actually gets less dense, which is really unique among pretty much all materials on the earth, because most materials, when they go from a liquid to a solid, become more dense. As the molecules in water begin to slow down and freeze, they don't have enough energy to break the hydrogen bonds between them. Those bonds in ice are more stable than those that we find in liquid water, and you can think of them more as permanent bonds, whereas in liquid water, the bonds are always breaking and reforming. The stable bonds between water molecules at these lower temperatures lock the molecules into a crystalline lattice formation, and each molecule is bonded to 4 other molecules, whereas in liquid water, on average you get 3.2 bonds between one molecule and others. Some are bonded to 2, some are bonded to 3, some to 4, but on average it's 3.2. This difference is why ice is actually 10% less dense than liquid water. Now, if you think about it, the 4 bonds in ice create more space between the molecules, and that space becomes filled with air, and the ice becomes less dense. Whereas in liquid water, the molecules can pack closer together, become more dense, and this is why ice will float on water. If it didn't, life really wouldn't be possible, because the ice that was formed would sink to the bottom of an ocean or a lake and remain frozen, and ice would accumulate over time until eventually that body of water was frozen solid. But since ice does float, it allows for life on Earth to exist because we have liquid water all the time. And it also serves another purpose. The floating ice will insulate the water beneath it, and it will allow the temperature of that water to remain warm enough so that life can survive underneath it. The last property of water that we want to talk about is how water acts as a solvent. All that means is that when you put things into water, they dissolve. Now in these cases, water will act as the solvent or the dissolving agent. If we put something like sodium chloride into the water, it is referred to as the solute, or the thing that's being dissolved in the water. The combination of the solvent and the solute makes up a solution. Anything that dissolves in water is referred to as hydrophilic, or water-loving. And all hydrophilic substances are made up of polar molecules or ions. There are also a lot of things that do not dissolve in water, and those are referred to as hydrophobic or water-fearing. And all hydrophobic substances are made up of nonpolar molecules. If we look back up here at the image of the solution, we can understand how things dissolve in water. Sodium chloride will dissolve because it is made up of hydrophilic ions. At the surface of each grain of salt, the sodium and the chloride ions are exposed to the water. These ions and the water are equally attracted to each other because of opposite charges. The positive hydrogens are attracted to the negative chlorides, and the negative oxygens are attracted to the positive sodiums. As a result, the water molecules surround the ions, creating what we call a hydration shell, and shield the ions from one another and allow them to remain dissolved in solution. This also works for other polar molecules, such as a lysozyme. A hydration shell will form, and there will be hydrogen bonding between the water molecules and the polar molecule that forms the hydration shell and allows those polar molecules to stay dissolved in solution.